All right, let's dive right in. Today, we're basically going to become code breakers. We're talking about inverse functions, which might sound like just another math topic, but trust me, it's a secret code that's at work all around you every single day. Let's get into it. So think about it for a second. Every time you shop online and see that little padlock in your browser or send an email you want to keep private, there's some serious math happening in the background to lock it all down. What do you think that secret is? Yep, you got it. It's an inverse function. It's basically the master key that can perfectly undo a mathematical lock. Understanding this is huge, not just for your algebra class, but for how the entire secure internet works. So how does this actually work? Well, at its heart, an inverse function just does one thing. It reverses a process. If a function does something, its inverse does the exact opposite, taking you right back to where you started. It's literally the undo button for math. And here's the core idea, and it's actually really simple. Let's say you have a function, we'll call it f. You put a into it, and you get b odd. Well, it's inverse, and we write that with a little -1 symbol. Does the complete opposite. You feed it b, and it spits a right back out. A perfect reversal. Okay, that sounds cool in theory, right? But how do you find one of these things? The good news is there's a simple, totally reliable, 3-step blueprint. And this thing works every single time, no matter what kind of function you throw at it. And this is it, the whole game plan in 3 steps. First, you just replace the f of x with a y. It just makes the equation look cleaner. Second, and listen up, because this is the most important part, you physically swap the x in the y. And third, you just do the algebra to solve for your new y. That's it. That's the blueprint. All right, enough talk. Let's actually put this blueprint to work. We're going to start with a nice, simple linear function just to see how it feels. So here's our first target. We need to find the inverse of f of x equals 3x minus 7. We've got our 3-step blueprint. Let's go. Okay, step 1, change f of x to y. That gives us y equals 3x minus 7. Done. Now for the magic move. Step 2, swap the variables. The y becomes an x and the x becomes a y. And just like that, we're looking at x equals 3y minus 7. Seriously, that swap is the whole secret. And now step 3. We solve for our new y. And check this out, we're just undoing the original math. To get rid of that minus 7, we add 7 to both sides. To undo the times 3, we divide everything by 3. See? It's a perfect reversal. And there you have it. That new y is our inverse function. So the inverse of 3x minus 7 is x plus 7, all divided by 3. Our blueprint worked perfectly and took us straight to the answer. Okay, that was a good warm-up. But what happens when a function looks a little more intimidating? You know, with x on both the top and the bottom? Don't worry, the blueprint doesn't care. It still works perfectly. We just do the exact same thing. Replace f of x with y, and then make that crucial swap. The x and y trade places. And now we've got a new equation to solve. The setup is always the same. So solving for y here just takes a little more algebra. The main goal is to get all the terms with a y on one side and everything else on the other. Once we clear out that fraction and shuffle things around, we can pull out the y as a common factor, and we get this. Y times the quantity x minus 2 equals 3x plus 1. From there, it's just one last division to get y all by itself, and boom, there's our inverse function. See? Even with a trickier problem, that 3-step blueprint got us there without breaking a sweat. So we found the inverse. We think we're right. But in math, you want to be 100% sure, right? How can we actually prove that we cracked the code correctly? Well, there's an essential safety check we can run. This is called verifying by composition. Now, this looks a little wild, but the idea is so cool. If two functions are really inverses, when you plug one of them into the other, they should completely cancel each other out, leaving you with just x. And as you can see with our first example, it doesn't matter which way you do it, everything cancels out and you end up right back at x. That's how you know you nailed it. Now, this whole process is super reliable, but I've seen a couple of common traps that trip people up. Let's shine a light on them so you can just step right over them. So, take a quick guess. Of those 3 steps, where do you think most people mess up? You might think it's in the messy algebra at the end, but it's actually way earlier. This is it right here. The single biggest mistake is forgetting to swap the x and y first. People just start solving the original equation for x, but if you do that, all you're doing is rearranging the furniture. You haven't actually inverted the function. That swap in step 2 isn't just a step, it's the entire point. So let's just hammer this home. Pitfall number 1, you have to swap x and y before you solve for the new y. And number 2, don't skip the verification. It's such a fast safety check, and it'll catch any tiny algebra mistakes you might have made. And this brings us right back to where we started, with secret codes. Real-world encryption, the stuff that protects your bank account details online, is built on this exact idea. It uses a function to scramble information that's super easy to do but incredibly hard to reverse, unless you have the secret key. And that key is the inverse function. So now you have the blueprint. You have the key. This technique is going to help you unlock inverses for all kinds of functions down the road. Radicals, exponentials, you name it. You've got a seriously powerful new tool in your math toolkit. The only question left is, what are you going to unlock next?